In section 4.8, we studied the indefinite integral, which was just a way of saying write down the most general antiderivative for the function that is the integrand. So here I have what we had written down where I'm using f, big F, to represent any antiderivative of little f. So big F prime is little f. We also know some information now about areas. That we can find an area under a curve by taking a limit as n approaches infinity of a Riemann sum. Thinking about the inside of the sum here being the area of a rectangle, and adding a bunch of those rectangles together to get an approximation, and then going from an approximation to the exact area using the limit by letting the number of rectangles get larger and larger and larger and go towards infinity. Well, we also have used this kind of thinking to think about maybe our function being a velocity function, and then finding a distance traveled if our function was all positive, or displacement if part of the graph was below here the t-axis, now that I'm calling it v of t. But we also know that if the integrand here in my indefinite integral were velocity, then the antiderivative on this side would be position, right? And so it seems that there's a connection between these two ideas. It's in section 5.3 that we start seeing that connection. And in section 5.3, some of that connection is just notational. In section 5.4, we finally put it all together and see what the connection between these two ideas really is. But first, we need to define what we call the definite integral. So let f be a function that's defined on the closed interval AB. Then, the definite integral of f over AB is denoted by this collection of symbols. So I see something very similar to my indefinite integral, but now I'm given what we'll know as bounds on the integral. And that definite integral is equal to this limit of Riemann sums, provided the limit exists and does not change value based on the partition chosen or the choice of the C sub k's. Okay, so the definite integral has a connection to an area under a curve if my function is positive. If my function is not always positive, maybe it looks more like this, then it's that idea of net area, or displacement rather than total distance traveled. And I now understand it to come from this limit of a Riemann sum. Now, these restrictions here tell me that I don't get to pick a partition to purposefully get a certain value, that value of this definite integral should be the same no matter the partition. Now, we will learn some kinds of functions where we don't have to worry about that, some functions that we know are integrable. and that's a good word to write down here, when this limit exists and the integral from a to b of f of x dx exists, we say that f of x is integrable over the closed interval a, b. So when I say a function is integrable over a finite closed interval, I'm simply saying we can do this process and get a value. Now let's go through some of the notation and then work an example. Just like with the improper integral, this is our integral symbol. For a definite integral, we have a lower bound and an upper bound. The function is still called the integrand. And dx is still a differential operator that tells us the variable of integration. Okay, so when we write down this collection of symbols, I like to think of it as that kind of net area idea, right? That no matter what my graph looks like, I can think about this collection of symbols being whatever the difference in these two areas is, because that one's positive and that one would be negative. And if my function was always positive, then I could think about just getting a positive area. But the point I want to make here is that when I write this down, I should get a number, right? The definite integral has this connection to area or distance traveled or displacement, whereas the indefinite integral is just a way of writing down the most general antiderivative. So I need to be careful about what I'm dealing with, because it is sufficient instruction to tell someone to integrate. Without bounds, we give them the most general antiderivative. With bounds, we should give whoever's asking the question a number, a value, provided that such a value exists. So, we now know what an indefinite integral and a definite integral are. I thought we'd end this video with an example. And so I want to integrate this definite integral. And we could graph x squared plus x on the interval from 1 to 2. And what I would see is something that looks a bit like this. And from 1 to 2, I see that I should get a positive area. And that picture's not to scale at all, but at least I do understand that I'll be getting a positive number. My only tool right now for investigating this definite integral is to take a limit of Riemann sums. Now, it's a bit daunting right now, because to show you that this definite integral exists, I'd have to convince you not only that this limit exists, but would be the same limit no matter what we did in terms of the partition or the choice of CK. For purposes of this video, in this example, I want you to take my word for it that this function is integrable over the interval 1, 2. So whatever partition and whatever choice of sample point CK we pick on those subintervals, we would get the same number. And that gets us out of having to worry about that second part, just that if we pick any partition with any choice of sample point, we should be able to take that limit of Riemann sums. So now, what I really have is an example much like what we were dealing with in our last unit. Because now what I can do is write that definite integral down as a limit of some Riemann sums. And I want to let the partition have, in subintervals, all of equal width. So I know delta x will be b minus a over n. And I'm going to use the right-hand endpoints because I'm comfortable with those, and we've done a bunch of examples, and I know those right-hand endpoints would be a plus k times delta x. So I have delta x and I have my right-hand endpoints, and now I'm ready to work with my sum and see if we can't find the value of this definite integral. All right, so this goes in for x. Times delta x. Okay, so I need to simplify this sum, and then I need to take a limit. I think I'm going to leave this right here and just work on the sum on some scratch paper. And so I need to square this and then add this to it. So I'm going to go on and square this as I write it down here on my next board. Still times that delta x on the outside. All right, so I got some like terms on the inside. I also need to distribute that 1 over n through. All right, so 1 and 1 make 2. Divided by 1 over n is 2 over n. Plus 2k over n plus 1k over n is 3k over n, divided by n is 3 over n squared k's. And let's see, that just leaves my quadratic term. So I'll have k squared over n cubed, which I think I want to write down as 1 over n cubed times k squared. And so now I know what I need to do. I need to rewrite this as 3 separate sums and try to use my sum rules. And I'm going to go on and pull out constants as I do this. And now I can use the constant rule for the sum, the special formula I have for the sum of the first n whole numbers, and then the formula I have for the first n perfect squares. Okay, so here is now my formula that would give me an area approximation for any value of n I plugged in. And now I just need to plop it back over here and take a limit as n approaches infinity. So the limit as n approaches infinity of 2 plus 3 over n squared times n plus 1 all over 2. Plus n times n plus 1 times 2n plus 1 all over 6n cubed. Okay, so now I need to take a limit as n approaches infinity. So I have 2 plus, this is going to have a square term over a square term. The leading coefficients will be 3 and 2, so plus 3 over 2. Plus, I have a 2n cubed on top over that 6n cubed on the bottom, so that's 2 over 6 or 1/3. And when I add those together, I get 23 over 6. And so now I know that the value of this definite integral I started with is 23 over 6. Well, this is how you evaluate a definite integral using the definition of definite integral. Fortunately for us, there is another way of doing it that we'll study in section 5.4. Being able to do this hinges on the fact that this was an integrable function over 1 over 2, so I could use whatever partition and whatever sample points I wanted to.